Finally, our last family of lipids. And this last family of lipids are things called steroids. And I know what you're thinking, because it's what I think when I hear someone mention the word steroid. And a steroid, I always think of these bodybuilders in the gym trying to beef themselves up so they can flex those muscles on the beach in the summer months and ooh and ah all of the other people that are there on the beach, right? So these steroids, like Lance Armstrong, would pump them up and they would improve their physical performance. Steroids, though, it's not just gym rats. Steroids is a much broader classification of molecules, and steroids are very important in our everyday activities and in our diet as well. And steroids also involve the family of molecules known as hormones, and almost all hormones are steroids. Hormones are what we call chemical messengers, and these are organic compounds that are synthesized in glands and delivered by your bloodstream to target tissues. And because of that, hormones are a type of steroid. So things like testosterone, a lot of people don't really associate to a steroid for some reason, or estrogen, a lot of people don't associate with a steroid, but they are steroids. So if you know a little bit about hormone chemistry or the hormone molecule and the purpose of the hormones, then they do meet the definition of what we call a steroid. Now, steroids are nonpolar, and because of that, they are lipids. So steroids, of course, are nonpolar. This probably means that they are made up of hydrocarbons. This also probably means they're nonpolar in nature, so don't be surprised if you see some rings maybe on them. And their nonpolar character allows them to cross cell membranes. So cell membranes, they cross them, and that's very, very important to us because we need them to cross cell membranes so that they can leave the cells in which they're made and enter the target cells of where they need to go. Now, all steroids contain what we call a tetracyclic ring. Okay, so I'm going to write that over here to the side. A tetracyclic ring. And tetracyclic means 4 rings. So these 4 rings are all very common. We start with a cyclohexane here, and then right beside of it is another cyclohexane, and then up here at the top is another cyclohexane, and then over here to the side is going to be a cyclopentane ring. So this is the tetracyclic ring that makes a steroid up. And this is something that I would ask for on a test because I don't want you to memorize specific steroid structures. I think that's kind of silly. We're not going to take a look and memorize different steroids and their structures, but I want you to know the template of how all of these steroids are made, and this is the template. So what you're seeing on the screen is really the foundation for all of the steroids that are out there. So we see 3 6-membered rings and a 5-membered ring. So 6-membered, 6-membered, 6-member, and 5-membered. So there's some properties about these rings that we at least want to talk about a little bit so we can pretend like we got some type of education in lipid chemistry and in these steroids, and that's how to number these rings. These rings have certain numbers to them, and well, not numbers, but letters really. And if I take a look at this template that I have just made, this is referred to as ring A and ring B, ring C, and ring D. So that's going to be another test question. You know, draw the template for all steroids. There it is. And then number or put a letter on the rings, and you should be putting A, B, C, and D down. And then we can also talk about the actual numbering of the carbons that make this ring up, and that will also be a test question. So the number 1 carbon is going to start right here in ring A up at the very top, and this is number 2, number 3, number 4, number 5, number 6, number 7, number 8. Then you got to be careful because number 9 goes here, and then number 10 circles back around, and there's number 10. So continuously all the way around rings A and B, and then they close that up. And then carbon number 11 starts right here, and then it goes carbon 12, carbon 13, and then we go across to carbon 14, carbon 15, carbon 16, and finally carbon 17. So that will be another test question. Give me the numbering of the carbons in the ring system. And your job is to figure out that it starts at ring A right up here at the top, and it circles around, and then it goes back up to ring C at number 11 here, and then it weaves through to carbon number 17. Not only that, but some other stereochemistry properties that we can talk about when it concerns these tetracyclic rings is that all of the rings are transfused. So that basically means they're kind of flat, right? They are connected in equatorial bonds, and one goes up and the other one goes down, and that is why we call them trans. So when this begins to happen, the rings basically line up with each other, and they don't have really any big kinks in the molecule themselves. So if you take a look at the PowerPoint, this is going to give you an A, B, C, D, 1, 2, 3, a little bit clearer than I can maybe. So there it is into the PowerPoint lecture for you. And then over here to the side, you're going to see that all of these rings, 6-membered ring, 6-membered ring, 6-membered ring, 5-membered ring, are what we call transfused. Okay, so transfused is different than cis-fused. A cis-fused structure would have maybe this A ring, if that was attached in the cis formation, to basically bend down, and this thing would take a big sharp turn around the corner, a big kink in the molecule. And that's bad news. We don't want that to happen. So that's what we call cis-fused, but most of these rings are transfused because of that. Now here's the difference between the cis and the trans. So this is what we have for all of the steroids. This is what we do not see. So this one is an axial bond. It points straight down. This one's equatorial. This one goes down and to the left. And because this one points down and because that one points slightly down, this is what we call the cis formation, right? So this is a cis-fused ring. Well, over here on this side, this equatorial bond goes slightly up and out, and this equatorial bond goes slightly down and out. And because one goes up and one goes down, we call that trans, and we call that transfused. Because of that, these two rings are glued together, fused together in a trans formation, and these two rings are fused together in what we call a cis formation. So there's the difference between the two. Now, the steroids, they have many different groups on them. They can have many different groups on them. Many of them have groups at what we call the 10 and 13 positions, but we also see these functional groups everywhere on the molecule, and that's what this picture is basically showing you. So we can have methyl groups on here, we can have random alkyl groups on here, we can have hydrogens, we can show stereochemistry of these groups, we can have oxygens, we can have a number of different things. Alpha and beta will come back again. Beta substituents basically means the groups are on the same side as the angular methyl groups. And alpha substituents mean that the groups are on opposite sides as the angular methyl groups. So keep that in mind. The angular methyl groups are shown here in the picture. Angular methyl groups, well, here is one and here is one. So this methyl is pointed up and this methyl is pointed up. The same thing's happening here. Look at this. Angular methyl groups. This one's pointed up and this one's pointed up. So CH3 and H are trans to each other. We see that with solid and dashed wedges. And in this picture, the CH3 and the H's are cis to each other. And we see that with the representation of both of them having a solid wedge. So this is a little bit of insight into steroids. The most common type of steroid, of course, is going to be our cholesterol structure. But it's more than just cholesterol. There's actually quite a few different steroids that are out there. Cholesterol is just one of them, folks. So cholesterol is the precursor for all of the other steroids that we will see. It has 8 asymmetric centers, that means chiral carbons. Therefore, it has 256 different versions, but only one of them is found and made in nature. So this is our cholesterol structure here. So A, B, C, and D, we get some double bonds involved. We have some OH groups involved. We see maybe just an iso unit here on the end. 1, 2, 3, 4, 5, 6, 7, and 8. Total of 8 carbons up there. So we can start assigning properties to cholesterol, and we can look at it and it's evidently clear that this is nonpolar, and this nonpolar substance can travel through cell membranes and go through the cell membrane because it is nonpolar. It can also be trapped in this lipid bilayer. We've talked about the lipid bilayer before. Our polar heads are up here at the top, our nonpolar tails are in here in the center, and every now and then we get a scatterment of cholesterol molecules throughout the way. And this allows the cell membrane some flexibility. It allows it some movement. Cholesterol is made from something that we call squalene, and squalene is something that you have seen in instrumentation class. And squalene we used to talk about when we were talking about stationary phases and gas chromatography and other chromographic separations. Squalene is very commonly found in shark oil, and this is the precursor that we can use for the biosynthesis route to make cholesterol from. But cholesterol is not the only steroid. It's just the one that we are the most common with because it seems to us like we always have a very high intake of cholesterol in our diet. And you do not need any cholesterol in your diet. Your body makes all that it needs. Period. There's no question about it. The cholesterol that your body needs, it makes it when it needs it and it sends it out. There's no reason for us to involve cholesterol in our diet on a daily basis. It's just extra cholesterol that we put into our system. And this extra cholesterol can swim around in our blood vessels and can start building up in form of plaque on our arteries and inside of our walls. And then this can lead to heart attacks. And very often because of our diet, we see a very high level of prescription medication that are involving the statin drugs. And these statin drugs are supposed to target cholesterol and prevent the biosynthesis of cholesterol. And it's a multi-billion-dollar industry for pharmaceutical companies. So Mevacor and Zocor and Lipitor, all of these are what we call statin drugs. And a statin drug, S-T-A-T-I-N, targets this cholesterol, bad cholesterol, and hopefully eliminates it as much as it can from your diet, and it prevents the biosynthesis route from happening because of it. Other steroids, though, we have many different ones, many different versions, and one of these is something like cortisone. Cortisone is a steroid. You can see the similarity to cholesterol there, just not an iso unit with 8 carbons on it. Up here at the top, you actually see an OH group and a carbonyl and another OH group here. We also see what we call 5-alpha dihydrotestosterone, known as DHT, and this is the molecule that they have linked to baldness. Estradiol, progesterone, testosterone, all of these are sex hormones or regulates the difference between male and female. So these are steroids as well, and a lot of people don't really see that coming. And then you have your group of what we call bile acids.